Okay, so let's take another try at this screen capture option that was built already into my iPad. We're going to try for 10 minutes on Tom's recommendation for a nice little chunk of time for a pre-recorded lecture. This is a PDF that I would normally use for an example that I would do on a whiteboard, and the students would just have it for reference. But at least it would be useful to work through just to show the types of things that I might highlight or do in a pre-recorded lecture if I'm using a PDF that is fill in the blank or has some other things that I'm doing with it. So let's take a look at this column design example, or at least take a look at some of the tables that we would reference in the AISC Steel Construction Manual. So for example, for this particular example that I would do on the whiteboard, I would ask them, if we look at this table from the commentary, which of the cases, if we were trying to idealize them as, fixed pinned or pin-pinned or fixed or pinned with sidesway or fixed with sidesway, right? Which one would we categorize it as? And for this particular example, I think we would perhaps categorize as somewhere between case E and case F, perhaps. Although now I think I'm misremembering a little bit. I think it might be somewhere perhaps between C and F. But regardless, we might remind the students of this table and the different support conditions and talk about things like theoretical K value, right? The theoretical effective length, which for different cases, right? For case C is 1.0, for case E is 2.0, for case F is also 2.0, and this is based on the theory or the examples that we talked about in class previously. And then we might also take a look at and note that AISC also gives us a recommended design value when the ideal conditions are approximated. So in other words, we don't have a fictitious pin support, but for case F, we're saying we do, right? This sort of fictitious pin support located here with the lateral sidesway as shown here. So we would also talk about how, case C, for example, when we have idealized the end conditions, theoretical K values is 1.0, but the recommended design value is 1.2. Similarly for case E, right, the theoretical K value is 2.0, but the recommended value is 2.1. And then if we come back to case F again, 2.0 for the theoretical, but also 2.0 for the recommended design value. And we would have some conversation about why that is for these different types of cases and the different types of supports. So for this particular example, however, we are just using that table CA 7.1 as a kind of a guideline. Where do we expect the K factor to be for this particular beam column, for this particular column and the end restraint that we have at the beam column joints. So we would zoom in here, and given the properties that we have for the columns as well as the beams, we would take a look at this little diagram here, and we would talk about, all right, given the properties of the beams and columns framing into joint A, we can calculate our GA, which is equal to EI for the column, the summation of EI for the column over summation for EI of the beams, and we might calculate 3.0 for GA. Similarly, for joint B, we would come in here and calculate, let's say, 8.0 for that particular joint in terms of the joint restraint, and then draw a nice straight line between the two, and where K intersects, where that straight line intersects the K line, that is our effective length vector. And we might have a discussion about where this particular nomograph comes from. And we would say, all right, K, and this is specifically with respect to the x-axis, is equal to 2.2 according to this nomograph. All right, and then we have two things going on, right? So for this W-shaped column, or the I-shaped column that we have, right, we have a KY that is equal to 1.0, right? And so let's suppose that L is 14 feet, and that means our KYL is also 14 feet, right? It means that KXL is 2.2 times 14. But we also know from our from our class that in order to use table 4-1 for this particular for W shapes, we need to convert the KXL, or the strong axis effective length, for use in the table, right? So in other words, we need to calculate our KXL over RX over RY, which is 2.2 times 14 feet, divided by whatever the RX over RY is. And so, for example, here we have 1.59 showing here. So if we were to use that particular column section, right, we would put 1.59, and then we could calculate what that value is. And if this were an actual example, I would already have the number and I would fill that in accordingly. All right, and then we might use this table here to talk about, all right, if we were looking for a particular W shape, a W14 in particular, that is 50 KSI steel as shown up here. And let's say that the weak axis controlled, and let's say that our KYL is equal to, or in other words, our LC with respect to RY is equal to 15. And let's say that our PU was equal to 1100 kips. Then all we need to do is go across this 15 line, and let's suppose if we're designing for LRFD, we just need to find the first column, right, that is greater than or equal to 1100 kips, and it looks like that the W14 by 99 is the winner in this particular situation, right? So we might have something like that in our example, and then I might go to the next page and we say, all right, but what if we want to find a similar column capacity but with a W12? Our architect has told us, please try to use a column with a smaller footprint in the building. And so if we had, again, let's suppose that weak axis controlled and KYL is 15 feet, and again, if we say that our PU is 1100 kips, well, looks like we happen to have a W12 by 106 that looks like it would be the controlling or the winner in terms of a column section, a W12 section that would work for this particular design level. However, we would also talk about that's only if, right, the weak axis, LC, with respect to RY, is controlling. If we had strong axis design considerations, right, then we would have to come down here and we would have to look at the RX over RY value, and we would have to look at what is that KXL over RX RY, right, and we would have to make sure that whatever that calculates to be, right, that we have at least that capacity, or maybe we need to choose another shape. And we could have a conversation about, well, you know, is the W12 by 96, right, is a lighter section a potential possibility? And then we could talk about, well, you know, based on the fact that it has a different moment of inertia, or different values for the moment of inertia, right? That changes the g, which changes the effective length, which then changes the kxl over rxry, and so we have some different possibilities that we can explore here for the design. And then finally, in this example, we would talk about, well, let's take a look at some of these lighter shapes over here. If we turn the page in the manual, we would see W12s that are like W12 by 40, 45, and so on, right? And we would notice that as we get to longer lengths over here, we have no values listed for the column capacities. And why is that? Well, that has to do with this footnote here, which note the heavy line indicates that LC over RY is equal to or greater than 200, which means that the shape is too slender, right, to be an effective compression member. And so therefore AISC doesn't even give us any values, because in the specification it says that we should stick with compression members that have slenderness less than 200 for our designs. Okay, so I think that would be a reasonable, approximately 10-minute video segment for a pre-recorded lecture. So let's see how big this is and if this would be a viable option for when I am traveling.